Welcome back to Differential Calculus. In this video, I wanted to talk a little bit about sets of numbers. You are almost certainly familiar with some of the basic ideas in set theory, but depending on the path that you've taken to get to this course, you may or may not be familiar with the particular notation and terminology that we're going to be using this semester. So as a nice chance to make sure that everyone is on the same page to start, I want to go through and talk about that basic vocabulary and notation so that we can be successful as we move forward. Let me get my head out of the way, and we'll start with the definition of a set. A set is a collection of objects, which we call the elements of the set. And the basic notation here, if I have an object, let's call it X, and I want to claim that it is an element of some set, let's call it A, I'll write that as X, weird looking E symbol, and then A. And we'll read that as X is in A, or more verbosely, X is an element of A. Just from the notation here, the context tells us that X is an object and A is a set, because we can only talk about objects being elements of sets. There's no other way of dealing with that. I guess I should be technically precise for those of you who are going onward to eventually study further mathematics. You can have sets whose elements are themselves sets, and you can talk about a collection of sets as being objects themselves, but that makes you start wanting to tear your hair out, and we're not going to deal with that this semester. When it comes to talking about sets, the simplest way of dealing with that is what's known as roster notation. So if I have a set here, I'll call A, and let's say that set A is the single digit odd numbers, 1, 3, 5, 7, and 9. I can list those out in a roster. I surround that roster with curly braces, which in this context are referred to as set braces. And again, the context of seeing a list surrounded by curly braces tells you that the list is the elements of the set in roster form. A couple of things about sets. I'm not going to have you writing sets as often as you are reading sets, so it's not going to be that important in this course. But it's worth noting that the elements of a set are unordered. I wrote this set as 1, 3, 5, 7, 9. I could have just as easily written this set as 7, 5, 1, 9, 3. And it is the exact same set. There is nothing different about it. The other thing that I want to mention about sets is that no element can appear in a set more than once. So if I tried to write this set as 1, 3, 1, 5, 1, 9, 7, it looks like I suddenly squeezed extra elements in because the number 1 is being repeated. But again, the big takeaway here is don't do that. Elements of sets should never be written out more than once. Right, so we have a nice set here, set A. Let's take a look at a second set here, set B. Which is just going to be the first 5 counting numbers. 1, 2, 3, 4, and 5. When you have a couple of sets, there are some tools that you can use to work on combining the sets. The set union of A and B, the symbol is called the cup symbol or the set union symbol. It kind of looks like the letter U. It does not have a tail, but it mostly looks like the letter U. And A union B is the total collective. Everything gets pulled in, keeping in mind that we don't write things more than once. So set A has 1, 3, 5, 7, and 9. And then we look at set B. We've already named 1. We don't have to name it again. We include 2. We've already named 3. We don't have to include it again. We include 4. We've already got 5. There's our set. Depending on what you're trying to do with this, it might be useful to write it in order. But again, those two are the same set, and there's nothing wrong with writing it in whatever order you'd like to. Other thing that we often do with sets is look for the overlap between them. We call that the set intersection. Right. The symbol for the intersection vaguely looks like a lowercase n. It is called the cap symbol, and it is the set union symbol just flipped upside down. The set intersect asks us where there is the overlap. What elements appear in each of the two sets? And I know this is a little bit awkward to do with set A no longer on screen, but you should have it written in your notes. All right, there is a 1 in both sets. There is a 2 in B, but not in A, so that's out. There's a 3 in both sets. There's a 4 in B, but not A. That's not good enough. There is a 5 in both sets. There's a 7 in A that's not in B. There's a 9 in A that's not in B. The only elements that are in both of the sets are 1, 3, and 5. That is our set intersection. Another tool that we often think about when it comes to working with sets is the set comparison. All right, subsets. Normally we write our definitions using A and B, but we've already given those some specific names. So let's go to P and Q. Couple of things going on here. We say that P is a subset of Q, which we denote using this symbol that looks like an underlined lowercase c. Abbreviation IFF. We use this abbreviation very often in mathematics. It means if and only if. That tells us that if every element of P is also an element of Q, then we can use this notation P subset Q. And we can use this notation P subset Q only if every element of P is also an element of Q. Most definitions work that way, which is why the abbreviation IFF is so common. But unfortunately, a lot of properties only go one way. If this is true, then that is true. But it's always a way to get the second part true otherwise. So it's a powerful statement, and it's more powerful than you think right now, and that will build up quite a bit. The other thing that I want to mention here, if you've studied set theory in a previous course, you may have had an instructor who made a distinction between a subset using this symbol and a proper subset. In this particular course, we're not going to worry about that. And in fact, every subset is going to use this symbol. This is the only one we care about. But I did want to at least mention that if you have seen that before. A subset, as we've defined it, allows that Q is a subset of itself. Every element of Q is an element of Q. That's all it takes. There is a concept called a proper subset that is every subset except that one. There are parts of mathematics where it is incredibly important. Calculus just isn't one of them. So we're not going to see that anywhere else this semester. I wanted to mention it because if you have seen this before, I've often had students who are confused and saying, wait, I'm waiting for this last bit to come down. I know it's supposed to, just not this semester. The reason that I care about subsets right now is one of the nice things about the union and intersection. When you take the union of two elements, it is always going to be the case that A is a subset of A union B, and that B is a subset of A union B. You can check that just based on what we've seen here, right? Every element in A, 1, 3, 5, 7, and 9, is also an element of A union B. Every element of B, 1, 2, 3, 4, 5, is also an element of A union B. Intersections work much the same. A intersect B is a subset of A, and A intersect B is a subset of B. Now that we've got that notation down, let's go on to talk about some of the big sets. We'll start off with the natural numbers. Natural numbers are sometimes referred to as the counting numbers. They are literally the numbers you use when you count. The symbol for the natural numbers is this funny looking letter N. It is literally write the letter N and put an extra line somewhere in it. I usually use this part to put the extra line. I have seen some people in some font packages that put the extra line there instead. It all works the same. It's called a blackboard bold or a double stroke character, and N for natural numbers seems to make sense. Right. For our purposes, we can list out the natural numbers using roster notation. 1, 2, 3, and so on. One of my favorite things about talking about the natural numbers is that it is one of the big controversies in mathematics. I've actually gotten involved in heated online debates that go on for pages in discussion forums. 0, in my view, for the purposes of this course, is not an element of the natural numbers. We can say not an element by taking the element of symbol and just putting a slash through it. 0 is not a natural number. There are some situations, there are some applications where talking about 0 as a natural number makes the natural numbers more useful. There are some applications where talking about 0 as a natural number makes things messier. And it happens that for what we're going to be doing in calculus, having 0 not be a natural number is generally going to make our lives easier until we change our mind. So for those of you who are continuing onward, about halfway through Calc 2, well, 2/3 of the way through Calc 2, we're suddenly going to change our minds and we're going to say that 0 is a natural number. I'm not going to say much about it. It's just going to be a thing. We're going to accept it. We're going to move on. Just where it's useful, where it's not. And for today, it's a lot more useful to have it not. The next big set we need to talk about is the integers. The symbol for the integers is a blackboard bold Z. And it makes absolutely no sense why the symbol for integers would be Z until you learn that the ideas of set theory were first developed by German mathematicians in the late 1700s and early 1800s. And as I understand it, the German word for number or integer or something like that happens to start with the letter Z. So that's what they used. And again, for our purposes, that definition of the integers is good enough. -2, -1, 0, 1, 2, continuing onward forever in both directions. One of the interesting things that we can do with this definition is notice that the natural numbers are a subset of the integers. Every natural number is also an integer. That's kind of nifty, and that's good enough for us right now. Up next is the rational numbers. And the rational numbers are messy enough that we can't really list them out. So instead, I'm going to turn to a different tool known as set builder notation. Right. The rational numbers are represented using a blackboard bold letter Q, which makes very little sense again, but instead of thinking about rational, the terminology here is the quotient. Rational numbers are based around division. The result of doing division is a quotient, so that's where the Q comes from. Right. So rational numbers are fractions. We write fractions as something divided by something else. I will use P and Q. And then I'm going to put a vertical bar here. And I'm going to insist that P is an element of Z and Q is an element of N. Right? This first bit we read as the set of all fractions written p over q such that, and then read the rest. P is an element of z and q is an element of n. Right. So again, set braces, so we know it is a set. And then I give a generic form. And the generic form in this case is fractions written as p over q. And then the vertical line we call such that, and it tells us how to define p and q. This also gives us why having 0 not be a natural number is so important. Because I can just say that q is any natural number. I can divide by q, and I don't have to worry about dividing by 0. That's literally the reason that we choose the definition of natural numbers that does not include 0. Stupid, but it works, it's valuable, it's worthwhile to us. The last set that I want to talk about, let's try writing that a little bit more nicely. The last set I want to talk about is the real numbers, which are denoted using a Blackboard bold R. Um, you are at least somewhat familiar with the real numbers. I don't have a good definition to give you for the real numbers here. If you are interested, defining the real numbers is almost within your grasp right now. And um, in an honors version of calculus, one of the big ideas in the first unit is trying to come up with a definition of the real numbers that is actually usable. It's really messy, and it takes about 2 hours out of class that I'd rather spend on other things. But if you are interested, I'm happy to share that with you. Just get in contact with me. But the real numbers include all of the rational numbers. They include all of the other things as well, right? All of the decimals that do not represent fractions. And thinking about it as the decimal expansion of anything is probably a good way of thinking about the real numbers. That's kind of how we define them. Um, but then there's one last set that I want to mention here, which is at the same time the simplest, but also the most complicated set of the entire bunch. The empty set. The symbol for the empty set is a circle with a slash through it. And the empty set is the set that has no elements. Sometimes you'll see people just write it out with the curly braces right next to each other and nothing in between. That is the empty set. One of the things that I do have to mention, a set containing the empty set is a thing. It is not a thing we are going to touch in this course. Do not tell me that you have a set containing the empty set. I will not look favorably on it. For those of you who are done with math after calculus, that's never going to be a thing that matters to you. But for anyone who does continue onward to study for more mathematics, the set containing the empty set is actually the fundamental definition of arithmetic, of all things. So if you want to understand why arithmetic works and why numbers work, you can get there, but that's well beyond the scope of this course. Just to make sure that you are understanding all of the notation we have talked about successfully, what I would like you to do as a video check problem, write in roster notation set C, given as the set of all n in N such that n is less than 10 and n is greater than 3. So take a couple of minutes, see what you can do with that problem, and I'll see you in the next video.